Last question on the practice test, all right? Right, so what's the names of the code? It's basically like lab code, more or less. Hash function, lookup function, sort of probing function, Bayesian resolution. And hash calculates. Key to a hash value. Add function. And find the data. Hash probe functions. And probe includes resolutions, all about where the data is. If there was a collision. All right, add new data to the array. Things along those lines. Yes, deleting is also a thing to mention. The remove data is also needed. Parity bit. Parity bit is a single bit value that is used to help validate data integrity. The payload. There are two forms of parity, even and odd. We'll use even parity and default. So we'll have X bits of a data payload. We will append a bit to that payload. The value of the bit we add is determined by the number of on bits in that data payload. So the objective is to have an even number of bits between the data and parity bit. All right, so And say our data is 3 0 bits. That's 0 number of on bits. Parity bit that we would use to set that will also be 0. So total number of on bits would be 0, 0 being even. If our data section has 1 on bit, we would set the parity to 1. Thus, our combined data has an even number of on bits. Right, so if we have 1 bit on in the data section, then we will set the parity bit to 1. And I'm doing just appending that parity bit into our data. We have 2 bits on in the original data, and the parity would be set to 0, leaving us with an even number of bits on, 2 bits being even. You know, the various ways that might have 2 bits on. All right, so 0 bits, 1 bit, 2 bits, and then all 3 bits. Giving us 4 on bits in total, 4 being even. Now seeing that there were 3 data bits. Now the number of bits of data isn't always going to be 3. We might have 5 data bits. There's 1 on bits. We need to set the parity to 1. Wherever that on bit may be, if there's an odd number, we set the parity to 1 to make the total combined data even. All right, so when storing or transmitting data, parity can be added in the storage system or the receiving system processes the data and inspect the parity of that data and see if I believe there's integrity in that data. All right, so if we go ahead and grab real world, we're building up right now parity that's pretty much foundational. There are going to be systems that will build on top of it, so we'll get to that very quickly. All right, so let's say we have data storage, and we're writing data to a disk. We're writing 3 data bits and 1 parity bit to go with it. What we should have on disk is 4 zeros. If when we go ahead and read back from the disk that data, and we see that we have a section of data where we have 1 on bit, that's an odd parity, and since we're using an even parity bit system, we can detect that there's something wrong with the data. At this point, it's possible we might be, okay, we need where the source data was generated from, go recollect that data, but we don't know what's wrong with the data other than it's wrong. So if our data is stored and then processed, we look at the data and find that it's not matching, and we can see if the integrity passes. Problem with parity bit, just a single parity bit, is that it is not good at even swaps. Right now, this data block has 4 ones. That's an even parity. Parity is correct, but the data that it should be representing is not matching what it actually was because we had 2 bits get flipped here. Right, the data corruption is a real problem. Noise can be introduced on the line when things are being transmitted between systems. Bits get flipped to on or to off from what they were before. Additional bits of data can get creeped into the thing. The idea of parity is it's all we can do is find out if integrity passes, and if it does pass, we can have some measure of confidence that the data is correct, but not a huge amount of integrity necessarily. So this one, yes, matches, and the data is correct, so our things are looking good. Now let's talk about we can use this. RAID, disk system. It's actually one of the topics I find most interesting. So this way of storing data, or talk about, is actually college students' master project thesis, something like that. There are a number of expansions of RAID. I do prefer this one. I've done a number of inexpensive disks. I find this one to be misleading because they're certainly not independent. They're definitely bound to each other. There are a number of RAID systems.
Since we've already,
let's see, where's Parity?
We already have interviews from
5, I
previous
think.
times.
Remember,
Survey to see
yeah, RAID 5
what people were hoping would happen.
is going to make use of Parity.
2 years ago is actually happening.
As is RAID 4. So the idea is okay, so we have the way RAID works is it's going to use multiple drives to store data. There are several schemes, and we'll take a look at them briefly. But some of the key advantages of RAID is you can get increased write speed, you can get increased read speed, you can get increased concurrency of disk operations, and you can also get data resiliency. So what we can do and right, say we have some data that we want to write to the disk. That data will likely be split across multiple disks. Say we have this 8 bits of data. And we get here. Text box. Right. Data 001001 disk. One of the things we'll tend to do is we're going to stripe the data, which means we'll break the write. Some of the data will get written to one disk, some of the data will get written to another disk. And over here on our parity disk, go ahead and calculate the parity for each of the bits. So the first bit of each data disk, so we have 0 and a 1, we use that to calculate the parity of that bit. And so in this example, we have a data block size of 2 effectively. Based on those 2 bits, we will set the parity to 0, we'll set to 1. Second 2 bits, we have 0, 0, so our parity is set to 0. We have 0, 0 again, and then we have a 1. And we'll write additional bits of data as well. Combinations. Writing additional blocks of data. And we'll calculate the parity and write the parity based on whatever the data blocks are. All right, so the next pieces of data will get split up. Those parts are written to disk, and as we write those parts to disk, we will calculate parity. So we have 0, 0, so that gives us 0 parity. We have 1, 0, so we get 1. We have 0, 1, gives us the 1. We have 1, 1, so it gives us a 0. Okay, the next block, see how we're doing if we're going to be writing these 2 groups of data. What is my parity block going to be? Just go ahead and write that down in the chat. Oh, yeah, I didn't hit the enter button. I pasted the link. Sorry about that. Calculate just 4 bits of parity based off of these 2 4-bit blocks of data. What should the parity be? Brandon's got a value there. Let's see if we get a few more people to type in. Same, we agree, different, we disagree. All right, we got 3 people agreeing. So 1 and 1, parities are even, so we'll set to 0. 1 and 0, that's odd, so set to 1. 0, 1's odd, set to 1, and 1 and 0 odd, so set that to 1.
I mean, definitely you can take the lead on explaining what the change is.
All right, so
but the rest of
there,
the analysis.
to the last block, just complete it out. There we have 0, 0 gives us 0, and 0, 1 for 1, 1, 1 for 0, and 0, 4040. So what we can do here is get data resiliency. If we have a drive die on us, say the Parity drive dies. Well, that's not a big deal, obviously, because the Parity drive was built off of the data that was in our 2 data disks. So if that drive dies, we put a new drive in, tell it to rebuild the data from our 2 data disks, and as long as these 2 drives don't die in the meantime, we'll go ahead and rebuild the drive, and we're back to a resilient state. Now, what if one of the 2 data disks dies? And this certainly happens. I had, what I have, read 10 or 01 on my previous machine. And I boot up one time, and Windows like, yeah, one of your disks is dead. Everything's all right. We can still do my job, do everything you're doing before. You just want to go ahead and make sure you replace that. And like a month later, I got around to actually replacing it because it's able to still recover what the data is from the remaining data disks. It's the same thing. So this can't read data from this disk anymore. This data is gone, it's corrupted, but I can still recalculate it, right? Just as we did before. I have 4 zeros, I have a 1 0 0 1. So in order for this parity bit to be 1, this data bit has to be 1. In order for this parity bit to 0, this data bit has to be 0 based off of the 4 bits of data I still have in my remaining data disk. Right, so we can come along, still use the system, a little bit of overhead now because now we have to calculate what the data is on the fly to read the data back out. But we can read the disk, and since we can determine what the data was that was on the disk that got corrupted or died, or just heads just started crashing, whatever is going on there, we can also rebuild it, and this one doesn't matter, they're the same thing. And so this is going to be one of the more common uses of just a straight out, just flat parity bit. So you have a parity drive. I think I say RAID 5 was integrated parity. So the parity may not necessarily be exclusively on a parity drive. The parity might be split out in other places. This is where we can make use of parity. Other RAID patterns are also interesting. Some of these will only give you performance, but not data integrity, which, depending on what the architecture of your system is going on, that might be what you want. You want the performance, but not the integrity, because the integrity is being handled by another part of the system somewhere else. Right, so striping, let's see, let me share it, where it's breaking the data across multiple disks. Right, so that means, say you have a 4 megabyte file that we want to write out. What we can do is we can go ahead and break apart the bits of data where a chunk of it gets written to disk 1, a chunk of it gets written to disk 2, a chunk of it gets written to disk 3, just like we're doing in my other example. That means instead of writing 4 megabytes of data serial manner to one disk, we can break that up across multiple disks. And so we have, 1 plus megabytes on disk 1, 1 plus megabytes on disk 2, 1 plus megabytes on disk 3, which means it's going to write much quicker because you're physically writing less data to any given disk. Right? If a disk has, like a 10 megabit per second write speed or something like that, instead of it taking 0.4 seconds to write to a single disk, it should take roughly 0.1 second to write that 4 megabyte data to disk, because it's only because it's splitting the load across multiple drives. Mirroring, it's actually an image now. Mirroring means basically it's a live backup. So instead of the data being striped across. These drives usually have a mirror, so I would have A1, A2, A3, A4, et cetera. So they're all on disk one, then I have the same thing over here, just two, A1, A2, A3, A4. Same thing twice. So you're not going to get any increased performance on writing to disk because the same data is being written is just being done in parallel to the disks. So it's still going to take the same 0.4 seconds, but you have increased read speed because you have multiple disks that can serve up the data, and you've got more. And by the increased speed, talking about more concurrency and possibly, depending on the controller of the system, possibly even faster that way. But mostly on the multiple concurrency, so you can actually be reading multiple files literally at the same time back into the system, whereas on a regular single platter disk, right, you can only ever be reading one disk at a time. You're reading that disk, feed to the buffer. If you have multiple applications that want to read disk at the same time, right, it's just like with the processor. If you have a single processor, and multiple processes don't run at the same time, they're just going to have to share the resource by going back and forth. Like here's a megabyte to the first requester, but even though it wants more data, then go pull a megabyte from another disk, or 4 kilobytes, 16 kilobytes, whatever the buffer size is going to be for any individual read operation, and send that along to the requester. Very often you'll see, if you look at some computer systems, the RAID is built in the motherboards. It's fairly common these days. 20 years ago, it was very uncommon. You actually have to buy a separate controller card for that. You'll see RAID 0, RAID 1, RAID 1 plus 0, RAID 0 plus 1. And sometimes they just say 1 plus 0 is RAID 10. There's no such thing as RAID 10. That's just 1 plus 0. Right, so you can combine these. So with RAID 1, where we have the mirroring that we were just talking about, it gives us the data integrity, but we can go ahead and combine these as well. So if we have 4 disks, what you can do is you can have mirrors of stripes or stripes of mirrors, which is the 0 plus 1 or the 1 plus 0. They're slightly different, largely the same, so that you can get both the data integrity as well as the performance gain by having the composition. But, systems, RAID 5, I think, is one of the more common ones. And I think in bigger systems, right here's the 0, 1, 1, 0 I was talking about earlier. Let's see, RAID 6, I'm forgetting. More 2 parity drives. Great, but if you have a large, very large server environment setup, you're definitely going to see RAID 5 more common, because the drawback of a RAID system is going to be you're wasting space. Just like with hash tables by design, we're going to throw away space for the sake of performance. With the exception of RAID 0, which is just the striping, any other RAID patterns, we're going to be adding parity via Hammond code parity or other mirroring type patterns. And that's what I'm talking about tonight. There's going to be some wasted space. So we're going to trade space for performance and, for reliability of the system. Because, losing your data tends to be unfortunate, depending on what the data is. And when Google first came into being, they changed the paradigm. Before Google, there were several search providers out there, but they're like a mainframe style thing. There's just a massive server. And as the number of requests came in, the load on the server increased, and the response time of the server precipitously dropped. So you could see when the server was busy and when the server wasn't busy based on the number of requests going through it, based on how long it took to get your results back. So what Google did was basically took like the RAID concept and had that as their computer architecture system. So there's an array of just machines and all the various web crawlers and all the various indexing operations go on very, very cheap machines. So basically, they're buying old servers. So like companies are buying new servers because their demand is increasing. So they'd be like, you couldn't use the old server anymore, and that's cool that they just bought all the old servers. And they found a way to just distribute the load across the server farm by having some of the data over in this various areas. It's just a matter of the server just being a gateway and directing the traffic to the appropriate node. And if the node died, they didn't much care, right? Replace the machine, have it recrawl that area of the internet that it was in charge of, and then rebuild the data, and then the backup online, because right, Google isn't the originator of that data. They're simply an aggregator of that data and a way to find that data in a quick fashion. Yeah, if the data in your system is that important where you want to, if a drive were to die at any instant in time, you want a RAID system on it, which means you have to have multiple disks. To support that, you want to make sure you have them on the board. Most of them do, last I checked.
How was the
Whatever script
the
you
old
need, doesn't
paper
matter.
shares? I'm trying to find it.
First one, let's see what
Yeah.
it says. Two. It just don't
Yeah.
fix. It's annoying when the page moves on you when you're trying to click on things. All right, so the RAID, this one supports 0, 1, and 1 plus 0. And you can 6 drives, so you can do all kinds of. And so 1 plus 0 is probably the way you want to go. Just remember, when you are doing this, if you're going to build a RAID system, the disks should be the same, because if you have, so you have 3 1 terabyte drives and a 2 terabyte drive lying around, you want to build a RAID with that 2 terabyte drive, we can only use 1 terabyte of that data because that 1 terabyte has to line up with the other 3 disks. So the smallest disks in the RAID partition are going to have to be, or is going to be the driver of how much. Like if you probably get another partition out of that other terabyte off on the side, you really need to space that badly, but you want the disks to all be the same spec, same manufacturer, same size, to the appropriate utilization out of those. All right, let's say it's the SATA RAID. I'm not sure there are any M2 RAIDs built on motherboards yet. Many motherboards do have the M2 slots now. But this is SATA RAID, and I don't have RAID in my current system. Anything that's really important, it's saved to the Google Drive. But it's just a spec. Everything else is
Yeah, I think it was an announcement.
not that critical. And that's, of course, just like the nature of the data drives the data structures that we might be using to represent and store our data. Same thing here with a RAID system. Do we need RAID at all? What's the nature of the data? Do we need data integrity? Do we need data performance? And then we can go from there to that. Yes, right. The parity bit is what is most useful here from our RAID disk system. How we're doing at the moment for our parity bits, and one of the things we can use it for is already asleep. Wow, it's early. All right. Talk about another use of bits. Coming code. Steal the table. So what we're doing here is we're using parity bit for our error detection. Data integrity. And we're doing so in an overlapping fashion. Nice table below here. Here has P X bits, our parity bits, and PX bits are the data bits. And so this table goes up to 15 data bits. What we can do is calculate bits up on here. Right, so we have our data bits. We have 0, 1, 1, 1, 1, 0, 1, carrying on, 1, 0, 1, 0, 2. I goofed up somewhere. 0, 0, 1. 9, 10, 11, 12, 0, 1, 0. 1, 2, 3, 4, 5, 6, 7, 15, 4, 8, 12. Oh, that's why I can't count to 15. All right. All right, and 0, 1. Right, so what happens here is the first parity bit is going to look at every other bit. So let's, and then calculate the parity. So let's break this table down. And this one is a little bit tedious. Trying to get everything all lined up. So parity one is to look at data one. Going to look at data two. Look at data four, data five, data 7, 9, 11, 12, and 14. And so based off of this subset of the data, calculate the parity. So when we're calculating parity, it doesn't matter how many bits of data there are. It could be one, it could be a dozen. Just count how many up are on, and we have 1, 2, 3, 4 on bits. So we'll go ahead and calculate that parity bit to be 0. Parity 2, it's also going to look at data 1, and you see we have a pattern here, right? So in the total payload, and we're inclusive of parity and data, you see parity 1 is doing every other position in the data. We get to parity 2, we're going to grow by a factor of 2, and we're going to be doing sets of 2, look at, skip, sets of 2, look at, skip, sets of 2, look at, skip, sets of 2, look at, that pattern. And then when we get to parity 4, same thing with sets of 4, parity 8 with a fourth parity bit, sets of 8, parity bit 16, sets of 16, sort of thing. So in parity 2, first data bit we look at is 1. We have 3 and 4. And we look at the table again, so just follow the pattern 6 and 7. We're just pulling down the data bits, so on and so forth. 10 and 11, and then 13, 14. And then we'll calculate the parity just looking at that subsection of data. 1, 2, 3, 4, 5 on bits. That parity bit gets set to 1. And we'll have our data bit. Those first 2 bits are parity. And we have our first data bit. And then the pattern would continue calculating out using the parity. This is far too tedious to do on a test. The important thing here to really know for the purposes of this class is the Hamming code is an application of parity bit. And the key thing that makes this useful is because of the overlapping coverage on the bits, the amount of corruption that's going to take before the message becomes durable and looks like a separate data block is going to have to be significant, because with overlapping nature, if I were to just change one of the 20 bits in this payload that we have here between the 15 data bits and the 5 parity bits, one or more of the parity bits are going to certainly choke at 1, right? So even a single parity bit would choke at 1 value being flipped, saying that there's something wrong with the data. Right? With a single parity bit, an even number of flips, if I have 15 data bits, I flip 2, 4, 6, 8, 10, 12, or 14 of those bits from what they were to the opposite, single parity bit would say parity passes. The check is passed, and we're as good as we can determine that we're good at that point. The overlapping data bits, let's see, with data bit 1, we have parity 1, parity 2 covering that data bit. Data 2 has 2 bits covering it, 3 has 2 bits, 4 has 3 covering it, 5 as a pair, right? We have 2 or 3 parity bits covering each position in the data segment of this payload, which means someone's going to complain. One of these parity bits is going to complain that there's some data corruption. Right? You read in on the article to find out how good it is. You can see we do have a 25% overhead. Right? Every 20 bits of data, 5 of that data is not actually data, but just parity. So there is overhead in any of these systems. Other systems are going to be far more ridiculous in the overhead. Let's see. Well, let's take a look at a simpler system. Repetition. Just replicate data and send that same payload next time. We'll use simple majority system to determine what the data is.
I think it's the one.
Right, so smallest being repetition 3, we'll replicate the data so that we have 3 copies of it. If our original data is 111, what we would send across the wire is 9 ones. Each group is in red. First bit in all 3 payloads is a 1, so we'll read a 1. Second and third bits are the same things. We'll read a 1, read a 1. Let me actually find out. So if payload will read the same, everything lines up. Type tonight.
Boys, go take your shower.
All right, this time we're going to have some data corruption. 1 bit got corrupted. When we read the data, we have a 0, 0, 0, the first 3 bits. 0 is the most common value, so that's what we'll read. Second. Second bit, we have 1, 1, 1. So we have consensus. Third bit, we have 1, 0, 0. Don't have consensus. The majority situation there is a 0. 2 out of the 3 bits say they're 0. So we're going with that. And we have corrected for the error. The first time there was no error detected, so there's no correction that need to be done. This time there's error correction, error detection, and error correction. And so the error correction is always going to be right. It's depending on where our data corruption is. We may or may not pick up on errors. Just depends on how much error there is in the data. All right, so this time I have to
Yeah, I can be open on Sunday.
go for underline bold. Seems to be hard to pick up on. 2 bits have been corrupted on the string. First bit, we have a 0, 0, and a 1. The majority is 0. Second one, we have 0, 1, 0. So it's 0 again. Then we have 1, 1, 1. So we're at 1 there. So we've detected
Happy birthday.
and corrected the error. Now, there's no guarantee that our error correction was the correct interpretation of the data. Let's say we have someone. Yeah, I don't know who that's my wife's in the meeting as well. She said happy birthday to it. Whoever it was, that was their birthday. Okay, this time around, still have 2 bits. That got corrupted.
Yeah.
Oops. This time the bits that got corrupted were in the same position. So this second corruption scenario, I had a corruption in bit position 2 and bit position 1. Since they were not in the same position, that data corruption did not cause a problem with the data read, but this time when we read our data, we detect that there is an error because we had a mismatch in bits, but we failed to correctly fix the data. We fixed it. We interpreted it as a 0 because we had 2 zeros and a 1, so the majority rules. But our correction was in error. So let's generalize. Error detection and correction. And so there are several schemes. Used to add data to the payload. Of data. I'm like saying data twice or can't think of a better word at the moment. It can be used to detect there's an error and possibly correct that error on the fly, depending on the scheme. And so if we have network communication as the means, the medium of the data flow, if all we have is error detection, we can do is request the data. Now, if we're downloading a resource, right, JavaScript, HTML, CSS, whatever that might be, that data is split apart into packets of data. Data packets have header that manages the routing of that data, as well as data for error detection. I can read up on you see there's a cyclic redundancy check. I need to use the acronym corrector. Cyclic redundancy check. Okay. Great. Seems to be working tonight. And there can be a lot of let's use Parity not too long. This version is using one Parity bit, which we know it does not have the greatest of yeah, it's a little more math-based, math intensive, but it's following the same ideas for checking out the data, right? In some schemes, I have, I'm pretty sure this got correction here. Right, some of the, and there are multiple schemes we can have correction. Single parity bit we can't correct the data because we have absolutely no idea which 1, 3, 5, 7 bits got flipped. I have error correction. If detection is not enough, because the additional delay of re-requesting packet, for example, would not solve the issue. Right, like streaming communication for this Zoom meeting, if a syllable or sound, I'm not too sure how much data in the voice and audio gets smashed together into a single packet, but we can't reorder the packets with a synchronous, using synchronous communication because we need it to come in the same order that it was sent in, because rearranging the words and letters obviously change the meaning. With a file that we're downloading, and if it's broken up into 2,000 packets, if I get packets 20 before through 50 before I get packets 1 through 10, it doesn't much matter. I can just collect all the pieces together. It's kind of like, you know, a Lego set. Doesn't much matter the order in which I pull the Legos out of the bag. I'll just start pulling them out, and as I get the right pieces for where I am in the construction of the set, I'll put those pieces together, and then the other pieces that I had set out and pull out and set aside, as I need those, and I'll go ahead and grab those and then put it all back together. Right. So with error detection, I can see I grabbed the wrong piece. I can take the piece off, go back to the bag, find the right piece because I grabbed a light gray when I meant to grab a dark gray or whatever. We can abide by those errors being detected at whichever point in time. If it's a serialized fashion, like we have with our meeting here, this is where we want to add more than just detection. Right, so adding in the error correction, you can allow it to be fixed on the fly keep the data flow, rolling downstream.
That was what we were asking about. You mentioned that, but yeah, we might figure it out more. as we
Right.
go through,
When you get into
but we can actually-
start taking numbering classes, you're going to learn more about CRC, TCP/IP stack, and where that's happening in that layer. There's a lot of different algorithms that can be used to make use of parity bits and other mathematical constructs like CRC is using to go ahead and check that the data makes sense, or where the corruption has to be significant for it to get passed, right? Because if you have a packet of 140 bits or whatever it is, all the various possible combinations that data can be sent, maybe we have 15 data bits, so you have 2 of 15 possible combinations of data that those 20 bits could be. If you happen to one of the other forms of that packet, then you get the wrong data is put there. And with 15 data bits, we did 16 data bits, right? That would be a Unicode character. So you have basically every Unicode character would be more or less the one little chunk there. Represent a single thing. And, they might get turned into a B or a C or something if you get enough of bits that are appropriately swapped. So it's not perfect. But it helps. Like somewhat along the threads of the security systems. If you have an unsecure system, right? Door is unlocked, so you just need to walk the door and enter it. But as the more complex the system gets, right, the more overhead that system is in general on things, but the greater security you get. Same thing here with error detection correction schemes. Those that can correct for the most errors are also going to have the most overhead, generally speaking, compared to other simpler patterns. All right. Good point. Time to pause. Go and take a 5-minute break. And we'll keep carrying on. All right. Questions about what we just talked about? Any questions about the other questions? Talking about the practice test, I noticed I didn't have an example of our memory management on there, so I did add a sample question onto the practice test. So I'm using best fit, worst fit, first fit algorithms for dynamically allocating in a fragmented heap area. So I did add one question here on to the practice test for test 5, that is next week. The final exam practice test is also available. So you can check that out, right? The practice test for the exam only talks about the new stuff, right? The final exam is comprehensive, as mentioned over here at the top. So the sample questions here are just for this last section 6 area that we've been talking about this week and last week. And so next week we have test 5 and we have review for the final. The way that the review for the final works is you need to go back and check on the things that have built up a little bit of rust and let me know what you want to talk about, what exercises, what areas you want to talk about again, and we'll just go ahead and talk about that to make sure that bring things back fresh into the mind. So there's no new materials next week that will be on the final in 2 weeks from today. The final is 2 hours and 10 minutes. That's pretty much the entirety of what we'll be doing on the 23rd. On the 16th, we have the test. We will go over test 5, and then we'll take the test, and depending on people finishing, so the 2 items we'll be doing is going over test 5 and then reviewing for the final exam. The questions on the final, it's about 45, 55 questions. Yep, all the chapters that we covered. Program 4. How are we doing here? I do have 2 submissions. That's good. Assume a few of people have it in progress. Yeah, similar questions as the other tests. Right, build a binary search tree with values in this set type thing. As we had before, build an AVL tree, or who's going to be alpha, who's going to be beta. Stack queue, O notation, of course. How are we doing from, we're reading from a file. There's C++. I know that's one of the things. People tend not to be overly familiar with, because file operations tends to be on the lower end of frequency for things that you often do. Anyone care to do some file I/O? We've already covered that in your previous courses and you're good to go. All I have left for tonight, we got through a little bit faster than I thought we would, is just, to program 4, try to get you unblocked anything you might be blocked on program 4. Looking back at the review for test 5, otherwise, next go to test 5, the review for the final, but there aren't, shouldn't be, unless I'll double check my notes. Maybe next time I might have one or two things that I did forget. Sometimes I like to forget and not remember in a timely fashion. I should rephrase that. I forget often, but most of the time I remember soon enough. Yeah, we should be done with section 6 of the course. I'll double check my notes. Again, I've checked my notes a couple of times a day just to make sure, but I believe I've hit all the bases that I wanted to hit, and then do extra. Check. No, make sure, right? We talked about all this good stuff throughout the semester. Right, annotation, recursion, sorting, right? We'll find all this stuff on the test. Nucleus trees, all our good graph stuff, tables, memory management, garbage collection. Yeah, we've got right, we've hit everything here. Yeah. Sure, it's not all entirely 5x5. Maybe at least we got a 4x4. At least in the case of the matrix. Test 5 covers section 5. Right, hashing being the largest bit. And we had all of these just on hashing. Then we have our garbage collection and the other memory concepts for the other bit of test 5. Yeah, preparing for the final, I'll just do now to go back to the old tests, try, recommend, look at the problem, answer the problem, check the answer, right? Don't just look at the problem, look at the answer, because that is not as good as a learning strategy to get things to stick. So reattempt the problem, then check your answer, because then if you did it wrong, you try to figure out what you did wrong and you figure it out. Note it as later. I would come back to it again later after you've gone through everything. So that go through everything once, see what you did wrong, and then go everything you did wrong a second time. And once you've got you feel stable there, then reread all of the lecture notes, because like 80 to 90% of the test, for the most part, comes from the lecture notes. And you recheck all your labs and exercises that you did throughout the semester, and then double check the book, make sure things are making sense for the chapters that we covered there. But yeah, that's the algorithm I would use for greatest utility of the time spent. So no one's interested in doing some IStream stuff, C++. We're good to go. All right. Yeah, IStream. So let's do a quick search here so you can do this here as a reference. That's pretty much what we're going to be doing. Ifstream. Ifstream is just is an input file stream. And several ways of reading from a file. I'll just steal from there. Incomplete type. That's interesting.
Band-Aid.
Oh, can you ask mommy, please?
Well, mom's in the shower.
Yeah, I'll help you in a little while. Let's see. Oh, that's true. Sorry, I was in C mode. C mode, standard IO. There's all that good stuff in it. All right. All right, so input stream was what we'll be using to read from our Borg file. So let's go ahead and create a file. Usually, with Visual Studio, the file that you can be reading from is going to be in the same folder as the executable. Sometimes when you're running the debugger, once you get the same folder of the project, yeah, you would create this file, and it would be your Borg program that you would run. Because we're creating an interpreter. And file extensions are just part of the file name, effectively. Something that the operating system uses. Just run this real quick, see if we're finding it. Seems we're not finding it. Let's see. So that's one of the first tricky things get squared away is make sure that you okay. Oh, so I don't. Oops. Bugs. Could not find the file. All right, let's go. Make sure I got my file name right. Cord.org. Move it over here to where my project file is. Try that again. All right, so that's where Visual Studio wants to find the file. So now we're reading my file contents. It's crushing all the white space and then dropping that onto the console. Now, one of the other ways we can go ahead and solve this right, if you like a getline sort of thing into the file path, you prompt user and just getline into the whole file path type thing. I haven't done a getline in a long time, so I forget what my getline syntax is. But go ahead and read the full file path, and then instead of doing just the file name, file path sort of thing, just need a C string. Let's load that up with a get line from the user. Then we have the file path, and then say the file. Right, so say the file name is wrong, right? Try to open up a file that doesn't exist. I couldn't find the file, code1.org. Right, so that's the first tricky part you want to address when reading from a file. It's actually being in the right place. Because right now, this is a relative path. So the relative path is going based off of where things are running. So if I were to run, back to debug, here's my executable. Command show. And run the program here. It's probably going locally here. Let's find out. Let's create the file and see if we can find it here. All right, so now it's finding the file and it's using this path to look for the file. And that's the basic behavior of anything. Like if I do a dir command, dir is in the system path, or dir is an executable on Windows. And you can find the dir command because it's in the path, but all of our other applications, right, like hope.exe, for example, if I try to run hope.exe here, it's be like, I don't know who you're talking about, right? Because it's just looking in, the basic behavior is look in this particular folder, this particular application. Since that's not in that folder, it does not know what to do with it. So that's one of the first tricky things to figure out on your system is where is the file? So if you don't know where things are happening, right, we just do like a dir command. And it's going to tell me what the context of our application is. So you can see here, this is the folder that's going to be looking for. If you're on a Mac, right there, or Unix, the ls, this isn't going to work very well on this system because it's not a Unix system, so it doesn't know what the ls command is. And I don't know what the Mac command is. So if you're on one of those other operating systems, this is a system command, just like dir is a Windows OS command. You're just sending command to the OS, and this will tell you where you are. And if that doesn't work, we can do an O stream. Sort of situation here. Let's see, is that good enough? Oh, yes, running somewhere, I guess. Where is my stuff? Okay. Let's see if that was enough to create. Right, so there it is. They created a file. It's an empty file, but there's another way of trying to figure out where it's trying to do the disk IO on your file system. Well, CD is change directory. What's the Mac? Let's see. It looks like ls, so they're using the same command as Unix Linux is doing. Not sure if it gives you all the details, but it looks like ls will work from Mac. I'll help you direct you to where the files are, and if all else fails, right, you can just tell the user to give it the fully qualified name and path, so they have to type whatever it is. Let me go back. Bed plus plus. Yeah, we call this one code 2. And we have the full file path, and the user types in the full file path from the command line. And we'll still be able to read things out. Right, so you can still find all the good stuff that's in the file. And from this point, it'd be like we talked about last week. Let's see. Let's talk about this. This getline will work better. Define line as a good old string. All right. All right, version 2 of our program. Now we're keeping all the full lines, right? So all our white space is intact. And I recommend using getline. So from getline, we can then break things apart. Okay. Let's see. Good enough. All right, we're going to assume the user is giving us good, well formatted. File input. All right, so you're at this point. Assume the code is working. And we just have keywords. So let me go grab. All right, here's my program, my board program. We got bar x equals 10. And var is our keyword. Right? And var is the important piece that we are going to be working on. All right, if we have if token, there's var. So we go ahead and process our variable. Else if. Proof. Into a variable. That's where we just need to fold in the hash table logic. Right, reading line by line can be fairly important for this program because with our code, we have two scenarios. We have a keyword is the very first token, or it's just a variable. As we want to change, let's make our program a little bit more complicated. Next, 25 and And that's basically just our else scenario. Modify the variable. In this case, we'll do token. Right, so first line code, we had a variable declaration. So we process the variable, we just do some more tokenizing. Then we had a print. Then we found our token is X. We're going to modify it, and then we're going to print it again. Right, and if we wanted to do further processing, this substring, right, this 0, that's where we started. So we go ahead and keep track of the last place, or you want to write a utility function. It's a tokenizer where you give it a string and it gives you back an array of strings. You need to go ahead and look at those. And I'm spoiled. I use C# whenever I'm writing code, generally speaking. It's got a nice little split function, just like Java does, just like a lot of languages do. But yeah, C++, I don't know why. Not in the standard library. Strtoke is C style of doing things. I mean, you could use that, but I mean you're using C strings, kind of a pain in the butt. Use Strtoke, but that would also work just as well. I mean, it's kind of bad to use a high-level language. You have to go back to mid-level language libraries actually do a basic thing like splitting a string. Whichever way you want to break it up, all good. Global variables. Global variables. Terrible. Right. They're kind of creating one here. Using a global variable. I don't recommend using global variables. There's some garbage left over after you do this later. But they're sort of doing the same thing. Manually splitting as we go, but yeah. Unfortunately, C++ is a little bit weak in the area for doing a string split. The other option, which I was forgetting about, which we've used in previous programs, was string stream. So you can do the getline. Actually, that's probably the better way to go. I'm thinking clearly. Right, you do your getline, you read the string, then you create a string stream from that line. You just read first item from the stream into token. Actually, let's just do it. String tokens line and all right, let's try the string stream, see how it's working. See what I broke. All right, broke it. What did I do? Because I'm stuck on input. Oh, that was interesting. Press key and then something magically happened. Or artifacts from last time. Okay. Process variable modify print. There we go. So that now at this point, process variable token. Let's see what I broke. That first one should be getting the equal signs. We'll do one more time. See if we're getting my variables out yet. So I got my equal sign. Let's see what I get there. All right, good work. That's interesting. Oh, that's right. I get the X name, get the name out first. Still had bar in there. Hopefully, this is giving you an idea. My kind of crude code here. All right, we got the tokens. We looked for token that was var. Code file. And the next one was X. Pulled out X as the value, so it should be the name of there's we go ahead. Equal sign, there's the value of, and then we don't need any more at that point. Name of X, value of 10. Line up with our code file here. Actually, I have 1, 2, 3, 4 pieces of data on this line of code. The first read of the line got the first token. Second read gets us the variable name. The third read pulls out that equal sign. And then the fourth read is giving us the value of the variable. When we get to the print one, I would just need one more extraction from tokens to get the variable name, and then we can do our lookup. But that's the general idea for the engine of the interpreter. The rest of it is building out your hash table with chaining. Questions about anything? All right. Should be our final bit of lecture materials. Everything else is as I laid out earlier. It's like we're going to get done early tonight. If you have questions, you're getting stuck on your code, or just ping me so I can help you get past whatever wall it might be. And carry on. Still have till next Wednesday to get this last program in. Otherwise, I'll just see you next week. All right, good night.